understood that sometimes when I talk about during my lecture, maybe I say the word and you maybe not understand exactly what I'm talking because of our accent, just English accent. So sometimes I will use this paper just from the paper. You can just follow the word I say, but I will do the calculation on the whiteboard. So I want to remember that what we talked last lecture. So the last lecture all was about the stationary conditions. So we categorize the model by that. So the first category of the system was when the density of the particle in the density of the state in the phase space was a constant microcanonical, and you, as we explained it, that the omega E and V, the number of the accessible states, was h power it depends if the gas is three-dimensional, was that. And here you had the integral over the full Hamiltonian, full Hamiltonian of the particle is given in the range of that. And here you have a d3 NQ, d3 NB. And this is a 6-fold integral, actually, 6-fold integral. Yes? Integral. So, and because of that was very difficult to calculate, so we developed a way, and we say that, again I repeat because that's very important. We say that you can use the you can use the definition of the differential actually, and just write it this delta over h to n partial derivative with respect to E, the same integral, and just here you can use it instead of this you can use it just 0 to E, and normally it's always it reduced to find the volume of the 3n dimensional hypersurface in the momentum system. So today we are talking about the another possibility which we have. So it's why this is a question. The another possibility is that the rho can be function of the Hamiltonian, or as we will show that it could be written in terms of the exponential minus beta h. And this is a proportional, so you have some constant here to make this equation equal. So what's important is that this is the canonical ensemble or canonical system actually. And in canonical system, the parameter which is changing is the energy. So energy is varying in the range of any number. It could be from 0 to infinity. But as you see that here also, in the microcanonical, the macro states are given by the number of the particle volume and the fixed energy E. So in microcanonical, any parameter, energy is fixed for the system. But in the canonical, you have a probability of the finding of the different energy states of the system. So I wanted to try to start from here. So what is important in microcanonical in the canonical is that we have a probability of the finding, the different probability of the finding different energy in the whole system. So, and this thermodynamics is also equilibrium thermodynamics. So this is also in the regime of the equilibrium because it's satisfying the view with the question. Equilibrium means that again we consider that the system in the reservoir, so isolated system actually, no any interaction with the outside. And so we call it this universal system. So this is the whole universe, you can call it that. And you choose a part of the system. It could be, for example, one atomic system or any other things, and even it can be a part of the cosmos, cosmology, for example, cosmos. Anyway, this is a universal set. So in the sense of the set theory, in the mathematics, so this is our universal. And we choose a part of the system, we call it A. And this, and we say that this part of the system has the energy ER and the fixed at the temperature T. The other part of the system will have the energy called E prime R, and it's still in the temperature of the T, because it's still according to the equilibrium condition. So the T for the system A should be equal to the T for the completeness part or for the other part of the system. Parts of system. It's should be the same, but the energy can be different. But the total energy is still fixed. So ER plus E prime R is fixed. E0. E0 is the total energy of the system, and this is a constant. That's constant. Actually, because the system is very large, so even if you part of the system and you give it the energy ER to that, so this ER comparison to the total E is negligible. So ER with respect to the E0, also that's negligible. So we can say that 1 minus R. So now I want to find the probability. The aim is for finding the probability of the system A to be found at energy, any energy, we can call it that. We use it ER, okay, ER. Or from other point, if you know the energy of that, we know exactly that. So except this energy, the other part of the system has different energy. So different energy is given by the subtraction of the energy of this part of the system from the whole energy of the system, E0 minus ER. So here you have a different possibility of the energy E prime R. So this R is the index. I mean, it could be just one. So in your system you have a number of this piece. But this is like one hydrogen atom, for example. I didn't make it several like that. Just I take it one. So you have several sets like ERT, E1T, E2T, E3T, and the other. So the other part of the system has the rest of the energy. So if you consider just a part of that, and if you tell that the energy is ER, so the question is that what's the probability of the finding another part of the system at the different energy? Maybe this question is not very well defined, but you will see that this is finding the probability of the other part of the system in the different energy. It reduced to the definition of the accessible state. You will see that there. So you know that if you want to find one energy state in the system, so if you have a more possibility, so you have a more probability, more chance to find that energy. If you have just 3 energy level and you want to choose very special value of the energy, so you have a less number of the possibilities. So if you have a very huge number range of the energy, so the probability of the finding a specific value of the energy will be higher than when you have a lower possibility. So we say that the PA, PAR, this is the probability of the finding system at energy E prime R. This is a proportional to the accessible state system with the energy E prime R. And that's enough for us. You know, I just want to, you need to be sure that to finding a specific energy, it's better for you to have a more possibility, more possible state. You remember that question I told you, and you always had the difficulty. When you have a 3 energy level, you remember that question in homework. And I asked it for you to find different way which you can find the specific energy. So some of you find it that for some total energy state, it's impossible to find. I don't know, for example, 7, you cannot make a 7 from here, or maybe you can, or 11. That was because of that, because number of the energy level was low. So if I give you 20 possibility, so with 20 possibility, you have many choice. You can find energy, any energy with that. But that is the idea here, you know. If you wanted to find a very special energy, exactly remember that question I told you. So you want to find the energy of, I don't know, 11, for example. So we have a few possibilities. If it's few possibilities, you cannot do that. So first of all, the probability, the possibility to finding that energy is related to the number of the accessible states. If you cannot if you cannot arrange the energy level to get that specific value of the energy, so it means that you don't have any more chance. So this chance is related to this number of the possibility you have. Exactly remember this question I told you. This is exactly like that. And that E0, this energy which I was looking, was like, for example, 7 electron-volt, and you have a 3 level. Exactly this question is like that. But the possibility, the change here is that we need to keep the total energy of the system fixed. So anyway, this is very related to that. I want to tell you now one thing, is that that's the only thing which had importance for me. So I can write that. Is prime, you can, for prime it means that because of the rest of the system we call it the energy E prime. You can call it this, I don't know, E1, E2. No any difference. Because of the conservation, because the system is in equilibrium, so
ER plus E.
yes. You can just replace the E prime R, any other energy level except the one which you fix it as this equation. And if you want to find the maximum probability, we needed to make the derivative of this with respect to the ER0. And it could be 0 in some value, we call it the average of the energy. We don't know exactly when this peak will appear, if this is an ER and this is a PRAER, which is proportional to omega prime R, it will have the maximum in some value, and We don't know that, but we say that it will happen in some point, and this is the maximum point for to have the maximum probability. So because these functions are exponentially and they are factorial and something, so to making the derivative is better to make the logarithm of those. So we make a logarithm omega e prime is minus er d. So just taking the derivative of these equations, so you use the Taylor series. So f x plus a is just f x, f r plus f prime r, 1 factorial x minus a plus the second derivative. But that was my question when I was studying that. Why we don't consider the second derivative? Because the fluctuation is very the fluctuation in the energy is considered very tiny number, yes, very small. We are expecting that the system reach the maximum probability, or you can find this energy level which you are looking after finite time actually. You don't need it to wait very long time to find it that. So it's related to the some type is related to the time or temperature. We don't talk about that. So you see that I don't want to repeat it that here. So just you can make it the Taylor series from this equation. And you can show that you can find it that in the some average of entities. So the first term, we need to be very careful because when you convert your function to that, this looks like your a and this looks like your x if you want to make your Taylor series, r plus x, because your variable is minus here. And that's the reason that here when you take the derivative 1 minus will appear. Partial derivative of logarithm omega with respect to the e, you know this from the first chapter. This is a 1 over kt, because in the box you remember that was the definition of entropy, yes? So partial derivative of that with respect to the e was, yes, 1 over t. So was partial derivative of this with respect to k b ln omega. So partial derivative ln omega with respect to e, you can write it that, yes, 1 over kbt. And this 1 over kbt, we call it beta, but it's just optional. So that's all. So now you can find the probability. So the probability of defining the system in the definite energy is just proportional to this omega. What you find is the logarithm of the probability. So the original probability will be the exponential of the right-hand side of your Taylor series expansion. So you make it the Taylor series. So differential n p prime r e prime r e prime r is proportional to the first term is some constant. First term was ln omega prime e0. This is a constant number. Minus beta ER. And of course the higher order terms, like the second derivative of ln omega prime e0 minus prime r but we don't consider the second order derivative. So PAR, the probability of defining the system in the energy level of the EAR is exponential minus delta EAR. You can remove even the prime. So, this is I want to explain about the probability